Welcome to this lecture of formal models. Today we talk about bounded model checking, which is a technique that allows us to test properties formulated in temporal logic like LTL with the help of a SAT solver. Bounded model checking plays an important role in the formal verification of hardware and software. So you most likely have a chip in your phone or in your computer that has been checked with the technique of bounded model checking. So it's a very successful technique, although the idea behind it is rather simple, as we will see. And in the next lecture, we will also have a look at planning, which is a core topic in AI, and there we will see that there is a close relationship between the bounded model checking approach and the encodings of planning in propositional logic. Before we start with introducing the technique of bounded model checking, let us quickly recapitulate propositional logic. I know we talked about temporal logic a lot and there we implicitly use it, but now we will do propositional encodings, and therefore I would like to revisit propositional logic again in order to ensure that we all use the same terminology and talk about the same formulas. So we define the set L of well-formed propositional formulas as the smallest set, such that the truth constants top and bottom are in the set, that the atomic variables are in the set. P is the set of atoms, a finite, not necessarily finite set of atoms. These atoms are also called propositional variables. And if we have a formula that is a propositional formula, then the negation of it is a propositional formula. And if we have two formulas that are propositional formulas, then we can combine them with disjunction, conjunction, equivalence, implication, and maybe other operators, but these are the core operators that we will use. And this is the way how propositional formulas are formed and how we'll consider them. And then about the semantics, I will also go very quickly over it, as you should know this from the logic course. An assignment is a function that maps each variable to a Boolean value, and then based on this assignment we get this interpretation function, and this maps a formula to a truth value. The truth constant top is always true, the truth constant bottom is always false, so this is independent of the assignment. If we have a variable x, then we assign the value according to the given assignment. If we have a formula not phi, then this formula is true if and only if phi is false under the assignment, and the formula phi or psi is true if and only if phi is true or psi is true. The other connectives can be, the semantics of the other connectives is defined accordingly, and as you remember, we had this notion of functional completeness, saying that if we have a negation and disjunction, this is enough to express all other operators by using rules of De Morgan and some other rewriting rules. We call an assignment a satisfying assignment if the formula evaluates to true under this assignment, and we call a formula a falsifying assignment of a formula if the formula under consideration evaluates to false under this assignment. So we say an assignment satisfies a formula phi if phi evaluates to true under this assignment, and it falsifies a formula if phi evaluates to false under this assignment. And we call a satisfying assignment a model, and a falsifying assignment we call a counter model. Then some more terminology, such that we remember these concepts. When I speak about a literal, then I mean a variable or a negated variable. Could also be a negated, possibly negated truth constant. Here I have some examples of literals: x, not x, y, not y. Yeah, so often it's not important if the variable is negated or not. We just want to cover both cases, and therefore we call such an element a literal. So this is a variable or a negated variable. Here we already have an application of the notion of literal. A clause is a disjunction of literals. So we have a formula that combines formulas in disjunction with a disjunction. A unary clause is a clause of size 1. There we have only one literal in a clause. The empty clause is also denoted by bottom. It's false also from the semantics, while it makes sense that the empty clause is false. And here we have some example: x or y, not x or x prime, or not x double prime. Then the third clause is just the unit clause x, and the last clause is the unit clause not y. Yeah? So we have two unit clauses, a binary clause and a ternary clause here. We also have the dual of a clause, which is a conjunction of literals. This also has this notion of unary cube, a cube of size 1. The empty cube, which is then a cube of size 0, which is equivalent to top. And here we have examples: x and y, not x and x prime, and not x double prime. So here, instead of the disjunction symbols, we have the conjunction symbols. And here, for the unit cubes, we have literals x and not y. These are two unit cubes, and as you notice, these are not distinguishable from the unit clauses, and it depends on the context if we are considering unit clauses or unit cubes. The important thing about a cube is that it is closely related to assignments. So assignments can also be seen as conjunctions of literals. If a variable is set to true, then the positive variant of the literal is included. If a variable is set to false, then the negative variant of a literal is included. And we will add cubes to a formula in order to enforce values of certain variables. Yeah, but before we discuss this in more detail and also recapitulate the notion of BCP, let us also remember the Satz solver Limboole. This solver you maybe used already in the logic course, and the nice thing about Limboole is that it is a Satz solver for non-CNF formulas. I did not introduce the notion of non-CNF or of CNF. A CNF formula is a formula that has the structure which is as follows. We have simply a conjunction of clauses. Yeah? And every propositional formula can be represented by an equivalent formula in CNF, but this requires often this extra transformation step, and therefore it's very nice to have a solver that does not have this restriction and can process arbitrary formulas as we have introduced them in the syntax before, seen them in the syntax definition before. Yeah, here I have the grammar describing formulas that are accepted by Limboole. We have the equivalence symbol, we have implication here. We can also write it in the other direction, but usually we use this right arrow. Then we have disjunction with this pipe symbol, we have the conjunction symbol with this and symbol, negation is an exclamation mark, and we have parentheses. And this grammar gives also the rules of precedence. So what binds stronger? The negation binds stronger than the conjunction binds stronger than the disjunction binds stronger than the implication, and the implication binds stronger than the equivalence. Yeah? So this is the syntax of Limboole, and let's have now a look at an example in order to remember how Limboole is used. You find the Satzsolver Limboole at the homepage fmv.jku.at/Limboole, and there you can download the source code. You can download binaries for Windows, Mac or Linux. And remember, Limboole is a tool that does not have a GUI, so you have to run it in a console and either directly enter a formula or give a text file as an input. Now we also have a web interface for Limboole, so you do not have to install and download the tool, but you can directly use it on this web page here. You find the link also on the Limboole web page, so you have Limboole to go. And in order to check satisfiability of the formula, you choose satisfiability checking. You could also check validity, which would check if all models are, if all assignments are model, but we want to know if one assignment is a model. Okay, and then you can directly enter the formula. So for example, let's try the formula A is equivalent to B. And if we run this, then we get one model. So for example, A is 0 and B is 0, so they have the same value. Now let's negate the formula and say they should be different. And if we now evaluate the formula, we get another model which says that A is false and B is false. Yeah, if we now modify the formulas and ask, is there a model such A and B are different and that A and B are the same, like that, then the solver says that the formula is unsatisfiable. What is also not too surprising, too much of a surprise. Yeah, and we could also then say this implies C, and this formula should be true because this part here is false, and then it's independent of the C. That happens now, and indeed we get some model, yeah, but could also be another model. Yeah, so this is how the syntax of Limboole look like, and we will use this solver for try out our encodings. From logic, you should also know the concept of binary constraint propagation, which is a very important technique for reasoning on formulas in conjunctive normal form. In other words, we have a formula which is a conjunction of clauses. And this formula contains a unit clause, C. So this clause contains only one literal. And then the value of the variable of the literal is set according to the polarity of the literal. And in the case of a C and F, it's very simple what is happening. If we apply this binary constraint propagation, we simply remove all clauses that contain the literal. So this means we set the literal to true. And we remove all occurrences of the negation of the literal. So we set the negation of the literal, so to say, to false. And important is that the application of PCP can trigger other applications of PCP. If we obtain the empty clause by PCP, then the formula is unsatisfiable. If PCP produces the empty C and F, then the formula is satisfiable. Let's look at some examples. Assume we have the formula phi, which is defined as A or B, and not A or not B, and A, so this formula is in C and F, and we have a unit clause here that contains the literal A. Hence, we can apply PCP phi A, and this gives us the first clause is removed. So we remove the first clause, and we remove the negated literal, and we remove also the last clause because it contains the A, and we get not B as a new formula. which is phi 2. Phi 2 is now also a single literal in a clause, so not B is unit, and we can apply PCB again on phi 2 and B not B. And now we remove this clause because we set not B to true, and therefore we get the empty formula. Yeah? Let's consider another example, which is as follows. We have the formula psi, which is A or B, and not A or B, and not B. Yeah, there we have also one unit clause, not B, so we can do BCP, C not B, and then we have to look, we remove this positive occurrence of B here and of B here, and we remove the last clause, and we get A and not A. Yeah, and A is a unit literal now, and not A is a unit literal now, so we can choose which of the two we propagate next. And yeah, it doesn't matter, yeah. It can be shown that PCB has a confluence property, meaning the order in which you apply PCB operations doesn't matter. So assume we apply A. What is happening then? Then we remove the first clause and we remove the literal from the second clause, and hence we get the empty clause. As the formula is in C and F and we have the empty clause in a conjunction, the whole formula is false. Yeah? So this is how PCB works on the formulas in C and F. Now what is if we have a formula not in C and F? And here we can generalize the idea as follows. If we have a formula of the structure where we have an arbitrary structure formula, phi, and on the top level a conjunction with a literal L, then we can assign L the value according to its polarity. Yeah, so we assign L a certain value. Let's again look at an example. Yeah, now we need a formula of arbitrary structure, not of C and F. Maybe let's have A implies B, and then on the top level we have A. And this formula is satisfiability equivalent to the following formula. So A is of positive polarity, therefore we say A, B, and A. We set A to true, and this when we set A to true, this is now the same as top implies B and top. Here we see we could not use another value than top because otherwise the formula would immediately be false. If we rewrite this is B, and then we have B as a top level symbol, we can set this to true and get again the same and get again a model, and can decide that a model, this formula has model A is true and B is true. Yeah? So we have to set A true because of this conjunction here, and if we set A to true, then it follows that also B has to be true, otherwise the formula would be false. Yeah? And this we could also simply prove with Limboole. I will not do this now, but you can try it out. And yeah, the important thing is if we would have phi and say not x, then x needs to be false, otherwise the whole formula would immediately be false. So there is not really a choice on how to select the value of x. And the important thing is, why did I write satisfiability equivalent and not equivalent? Two formulas are equivalent if they have the same models, and they are satisfiability equivalent if the one formula is satisfiable if and only if the other formula is satisfiable, and often this property is enough. And here in the second formula we do not have any occurrence of a if we remove it. So it can be that we find a model, or this model, this formula here, this formula B here has as model also the assignment B is set to true and A is set to false. Doesn't matter because the A doesn't occur here, and this is then obviously not the model of the formula here. So we just have satisfiability equivalence through the rewriting. Okay, and that was my short introduction into propositional logic, and I think with this we are equipped with all the concepts we need in order to introduce bounded model checking and to use a SAT solver to perform bounded model checking. The idea behind the technique of model checking is very simple. On the one hand, we have the implementation, which can be some hardware or some software, which we want to have correct. And what we do is we build a formal model of this implementation that describes it. For this we can use, for example, Kripke structures, as we have seen them in the previous lecture. On the other hand, we have the requirements the implementation should fulfill, and these we express in terms of a formal specification, which we can express with a temporal formula, for example in LTL, as we also have introduced in the previous lectures. And then we take this formal specification and the model of the implementation, put it in the model checker, and see what the model checker tells us about it. And if we are lucky and the implementation is correct, then the model checker can prove that in all execution possibilities the implementation satisfies the requirements, so that the kind of properties that are described by the specifications always hold. Then we can trust the software that it indeed satisfies these properties which we want to have. In case there is an error in the implementation, the model checker detects this error, and the nice thing is the model checker not only says there is an error, but it also gives an error trace which leads us to the problem, so which gives us an execution sequence that tells us why how we have to execute the program in order to reproduce the problem. And there are different ways how model checking problems can be formulated and solved, but they all have in common that they want to answer the following question: given a system K, here can be hardware or software, and the property P, does property P hold for the system? So is it true for all execution possibilities that starts at the initial states of this system? And there are different ways how model checking can be done. On the one hand, it can be done as explicit state model checking. There the enumeration of the state space is done explicitly, and very good search algorithms are applied. More details on that you will hear in the course Model Checking, which is both a master course, both in the AI study as well as in the computer science curriculum. And there you will learn the implementation techniques and optimization techniques in order to deal with the states explosion problem. Because if you think about it, then even a small program has very a lot of states, yeah, and it's important to use clever search techniques that deal with this huge search space in order to get a solution overall. And the alternative way of performing model checking is to follow a symbolic approach, what we will do in the following. Here the idea is to represent the model checking problem as a logical formula, for example in SAT or in QBF, which is the extension of SAT with quantifiers, which allows a more succinct encoding of the model checking problem, or in SMT if different kinds of variable types are needed. And but we will in this lecture focus on doing model checking with SAT. And for this purpose we have to have a look how we can represent a Kripke structure in terms of a propositional formula, and then we have to translate also the temporal formula or the property we want to check in terms of a property that that can be represented in SAT. And this has the big advantage that we do not need a dedicated solver for temporal logic, but we simply can use the SAT solver as a black box. And the intention is we have our encoding of the Kripke structure as a propositional formula, and of the property we want to check of the propositional formula, have it as a propositional formula. We give this to the SAT solver. If the SAT solver says the formula is unsatisfiable, then we know that the property holds in the system. Yeah, it's not violated. We will see why we ask for unsatisfiability later on. And if the formula is satisfiable, then the model of the formula we get from the SAT solver gives us the error trace. So it gives us the execution sequence, the sequence of execution steps that lead to the problematic state. And this we will do in the following. So the first thing is we have to encode the Kripke structure into SAT. In the context of model checking, there are different properties which can be considered, and here I have listed a couple of them which play an important role. So reachability asks if a property holds in one reachable state. This is closely related to safety property, which says, or which asks if some bad property P never holds, so if there is no state reachable in which P holds, which also says that which ensures that something bad will never happen, that the system will never crashes. Then there is invariant property, which asks if a property P holds in all reachable state, so if a property globally holds. And here we see that these property formulations are very closely related to the statements we could express in temporal logics, and therefore these temporal logics are very well suited for expressing these properties a system should satisfy. Then two more properties are liveness and fairness. Liveness asks if something good will, or ensures that something good will eventually happen, so that the lift will come. And fairness says that under certain conditions some property holds repeatedly, so here it's ensured that some process never starves, for example. Okay, and now let's come back to the example we have seen before, the example of mutual exclusion. We're given two processes, P and Q, and they share a resource R. And if the resource R is accessed by process P, then the property small p is true, and if R is accessed by Q, then property Q is true. And this behavior we model by the Kripke structure. Yeah, we have already seen this. And we are interested in asking, is it possible to reach a state such that P and Q hold at the same time. So finally P and Q are formulated as LTL formula. And if you think back, we have said yes, after 2 steps we reach state D, and in this state D both processes access the same resource, which we do not want to have. Yeah, but we will now see how we can find this automatically by a SAT solver. Again, I would like to point out that this example is very simple and could be easily solved by hand, but it conceptually shows how things work. If we would do a real-world example, it would be far too large and would not give any more information regarding the conceptual ideas behind this approach. Yeah? So we use this example as a running example. And what we now have to do is we have this Kripke structure, and we want to represent this as a propositional formula such that the SAT solver can decide which states are reachable from the initial state. Okay, and for this we need some terminology and also some background, how we can. So I would like to write this up as an algorithm, because this in the past helped a lot, or is easier to read for many of you, and therefore I have to introduce some notation in order to translate the Kripke structure into a propositional formula. So we are given a Kripke structure K, which has a set of states S, initial states, transition relation, and labeling function L, over alphabet A. And A contains n atoms, A1 to AN. And as we have done it also for identifying transitions for the I/O automaton, and also for identifying Kripke structures from circuits, we need current state variables and next state variables. Yeah, so we have to introduce variables that stand for the current state, and then we have the variables that stand for the next state. Yeah, and what we do with the propositional formula, we relate the current state variables with the next state variables. So first of all, the important question is, how do we represent a state? And we represent one state simply as a conjunction of literals. Of the literals from A, and if we have on the one hand, if we have a state S, then we want to have the variables, the current state variables, and we also want to have S as the next state variable. So first we represent S with the current state variables, with the variables from the set A, and this function current represents the state S as a conjunction of literals, such that a literal AI is positively, so a literal Li is a positive literal AI if AI is occurring in the labels of S, and if it's not occurring in the labels of S, then Li is the negation of AI. Yeah. So if in state S the atom AI holds, then it's positively added to the conjunction of the literals, otherwise it's done negatively. And we do the same for if we represent the state S as a next state, but here we take the primed variables. So we add so we build a conjunction of the literals k1 to kn, where ki is a prime I, if ai is in the labels of S, and otherwise ki is not ai prime. And with these two functions, we want to define a propositional formula T over this variable a and a prime, such that for all states Si and Sj it holds that the formula T and current Si and next Sj is satisfiable if and only if we can make a step from Si to Sj in the Kripke structure. Yeah, and here, what does this mean? We have here this T, which is the transition relation encoded as propositional formula over the variables a and a prime, and here current Si and next Sj are cubes. Current Si is over the variables of a, next Sj is over the variables of a prime, and here we have conjunctively a lot of conjunctively added literals. Yeah, and as we have seen before, this enforces the values of the variables if we have literals at the top level of a formula, because otherwise the formula would evaluate to false. And so we force the variables to a certain value. So we ask if Si is the current state and Sj is the next state, is it possible to make a step? And for this we need to encode the transition relation T in propositional logic. And so how can we do this? Here I have a very simple encoding which simply processes the Kripke structure. Here not much reasoning is done, and this is one way of doing it. It can also be done in another way, and we will see another way as well, but there are other options. There are more options how to do it, but this is one way how to construct this for propositional formula T. So we are given this Kripke structure over set of variables A, and we say A are the current state variables, and then we introduce or use also the A prime variables for the next state. Okay, and here we have some pseudocode which explains how we construct the transition, the propositional formula of a transition relation of a Kripke structure. And we do this as follows. As long as we have states in S, so we process all states, we select one state from S and remove this state from S. And for this state S, we have a look what are the direct successor states. And what we now do is we build the following formula, which says if we are in state S, so if S is the current state, then we construct this N, it says we are in one of the successor states. And what are the successor states? Here we have to take a look at the transition relation, and we have to figure out what are the states that are reachable from S. And for all these states which are reachable from S, which we call T, we add them as candidate for the successor states, for the next states. Yeah? So we start with the empty formula. So this is the case if no next state is reachable, but we said the transition relation doesn't have is total, so we can always proceed. And we conjunctively add all the successor states as next, all the successor states of S as next state. Yeah. So if S has two successors, we have successor 1 or successor 2, and then we add this to the to T. Yeah. So and we do this for every state, and what we add to T is if we're in state S, then one of the successor states has to be a successor state of S, and this we have collected in the N. Yeah? Let's have a look at an example. Here we have again our Kripke structure, and now we proceed and consider all states. I indicated with the colors which states the variables are referring to in order to make the mapping easier. In state A, both P and Q are false. Yeah? So now we are building the implication for state A. If we are in state A, then the successor states are state C, which is not P and Q. And as this is the successor state, we have to prime it. And the other successor state is state B, which is P and not Q. And again, we have to prime it. Yeah, and this we now do for all states. If we are in state P, which is P and not Q, then the successor states are A or D. If we are in state C, then there is only one successor state, which is A. And if we are in state D, there is only one successor state, which is again A. And this is one step in the transition relation we have for this Kripke structure. And now let's have a look what the Satzsolver makes out of it. I have now copied the formula into the input window, into the input field of Limboole. So we have here the formula I just showed you on the slide. As I cannot enter the prime here for the input of Limboole, I renamed the next state variable with minus next. So here we have on the left hand side of the implication the current state variables, and then on the right hand side we have the successor variables. And now we can ask Limboole if this formula is satisfiable at all, and it says yes, it is satisfiable, and it says from state 1, 1 we can make a step to state 0, 0. And if we look at the Kripke structure, then this is this transition here. So from state 0, 0 from state 1, 1, which is state D, we can indeed make one step to transition. We can indeed make one step to state where both P and Q are false. So we can go to state A from state D. And now we might also want to fix the state where we want to start. So maybe we do not want to start with state D or make the step from state D. But we want to say that we want to start in state A. Therefore we say and P and Q. This enforces, and what I forgot is we have to say not P and not Q. This enforces that the variables P and Q are both set to false. And now we asked the Satzsolver again what is happening, and then indeed the current state is 0, 0, and the next state is 1, 0, which is 1, 0, which is state B. We could also now ask if we can do a step from state 0, 0 to state 1, 1. So then we would also enforce the values of P next and Q next. Now I add them positively. So what I'm asking now is, given this encoding of the transition relation, is it possible to make a step from state A to state D? And the answer should be no, this is not possible. And this is indeed the answer. Yeah. So here we now ask the SAT solver, can we do a step from state A to state D? And if we look at the Kripke structure, this is indeed not possible. Yeah, so this is one way how we can encode the Kripke structure. Another way or another approach, here on this slide I have again the code. You can also try out yourself. What is important, this I did not mention because I used Limboole in the web front end. If you use Limboole in the console and you want to check satisfiability, you have to use the -s option, otherwise it will check validity, but we want to check satisfiability. Yeah, and here I have an alternative encoding of the Kripke structure. What I do here is I do this transition table as we have also done it before. So here I have the current state variables, the 4 possibilities, and here I have the successor states. So from state 0, 0, I can go to 1, 0, or I can go to 0, 1. If there are multiple choices, then I have to add or duplicate the entries on the right hand side. Yeah, so here I have 1, 0 or 0, 1. Also in state B, in 1, 0, I have 2 ways to continue. I could go to 0, 0, I could go to 1, 1. If I'm in 0, 1, then I can go only to 0, 0, so we have same entries in both columns, and the same here for 1, 1. There is also only one option, therefore we have only one choice, and therefore we put here 0, 0 and here 0, 0 as well. Okay, and if we have this, we can encode the formula as propositional. We can encode this transition as propositional formula, and we have to say how P prime or Q prime is calculated from P and Q. And this, because this example is so small, we can do by looking at the table. So P prime is the formula which we have when there is a 1 in the line with 0, 0, and otherwise there is a 0. Therefore P prime is equivalent to not A and not Q. For Q prime the situation is very simple. We have just 0 here, so not Q is equivalent to 0, and we do then the same for the blue part here. P prime is equivalent to P and not Q. Yeah, so only in this line we have a 1, so it's P and not Q, and Q prime is simply equivalent to the negation of Q. Yeah? And when we have these two formulas, we can simply combine them by an OR and have a representation of the Kripke structure, which is more compact than the formula we have previously seen. And this formula we can also give to Limboole and use in a similar way as we have seen it before. Yeah. On this slide I have the encoding in Limboole syntax. Again, we have the P next variable for the next variable and the PQ variables for the current state variables. yeah, so we define p next as introduced before. Q next is equivalent to bottom, so it's simply not Q next. And then Limboole gives us, for example, a satisfying assignment where P is false, Q is false, P next is 1 and Q next is 0, which is this one step here. And yeah, otherwise it works very much as before. And now the question is how we can do multiple transition steps. So we do not want only to switch from one state to another, but we want to switch from one state to another, to another, to another state. And the question is now how can we achieve this with this encoding of the transition relation we have seen before. And the idea is rather simple. We copy the transition encoding and say we go from a state S0 to S1, and then from a state S1 to a state S2, and from a state S2 to a state S3, and so on. Yeah, and we can then use the help of the SAT solvers to see from which states we can proceed to the next states. And now how can we achieve this if we have the encoding of the transition relation in T? Now we can do one transition step if we say we go from a state S1 to S2. Yeah? Let's now parameterize the current state and the next state here, so that the first argument is the current state and the second argument is the next state. Yeah? And this is we go from a current state S0 to the next state S1. And then and this formula is defined over the variables a and a prime. And now we take a copy of t and rename the current variables to t prime and the next variables to double prime. And then we can say we go from state S1 to state S2. And then if we combine these two formulas, we can go from S0 to S2. Yeah? And how would this look in our example? So we take the formula from before. I take the short version. Here we have the variables without the primes and the variables with one prime, which are the current and the next state variables. And then we take a copy of the formula and we rename the variables. And each variable gets an additional prime. So the current variables of the previous step, next variables of the previous step become the current variables of the previous step. So we add one prime to the current variables, and the next variables become the next variables. So we double prime them. Yeah. So we can do one step and then two steps with this second formula here. And now let's have a look how this looks in Limboole. So we have the first copy, again with the P next, Q next, and PQ variables. This allows us to do one step. And then we have the P next 2 and P and Q next 2 variables. And what does this mean? I think here I have a bug in the coloring. So we start, we start here in this, no, I have no bug in the coloring. We start here in P is false and Q is true. Then we do one step, and after one step we are in state 0, 0, and after another step we are in state 1, 0. Yeah? And this we can read from the truth values of these variables. Yeah? The PQ variables give us the first state we are starting from. The P next and Q next give us the second state, so the first state which we reach after one step, and then we get the state which we reach after 2 steps. Let's have a look how this looks in Limboole. Now I use Limboole in a console, so I have the transition encoding here in a file. It's exactly the same as I have it here on the slides, and I call Limboole with the -s option. And what result do I get? It's a different one as I have here on the slides, so it seems that I used another version of Limboole for doing the slides. So we start in the step B, then we go with one step to state D, because B next is 1 and Q next is 1, and with another step we end up in A. Okay, and now I could also use the trick we have seen before in order to enforce Limboole to start in the initial state. So I say not P and not Q. And now what is my model I get? I get P and Q 0, both 0. This is the first step. Then with one step we go to 1, 0, which is B, and with another step we go back to A. And I could now ask, is it possible to be in say B again after 2 steps? So here I would have to say P next 2 and Q not Q next 2, and this should not be possible. Exactly, so with 2 steps I cannot reach B. If I remove the not here, then I would ask, is it possible to get to D in 2 steps? And obviously the answer is yes. We can go from 0, 0, so from state A to state B, and from state B we can go in and we can reach D in the next state. And in a similar way we can do 3 steps. We copy again the T encoding and have now 2 more lines with P next 3 and Q next 3 becoming the new next variables, and then P next 2 and Q next 2 are the current variables. And then we can check where can we go with 3 steps, and here I have a solution. If I do not do any restriction, we can say from state C, starting from state C, we can go to state A. From A we can go to B, and from B we can go to D. Yeah, so this means we have done 4 steps. And with this we have everything together we need for doing bounded model checking. And one question that can be answered with bounded model checking is as follows. We're given a Kripke structure K. Is there a path of length K to a bad state S in which a certain property is violated? In other words, we want to check, is there a path where globally P does not hold? And the important thing is, if globally P does not hold in a Kripke structure, there is a finite counterexample. So we have to reach the bad state at some point after K steps. And this is the main idea behind bounded model checking, and this is also where the bounded comes from in the name. We consider paths of a fixed length. So we do not consider arbitrary paths, but paths of a fixed length, and encode the K steps into a propositional formula together with the query, with the property that should hold, pass the problem to a SAT solver. If the formula is true, then we know that the bad state is reachable. If the formula is false, then we increase the k. Fortunately, modern SAT solvers are incremental, and this means that they can reuse information they already encountered in runs. Okay. And here we have the full formulation of the bounded model checking problem. So given a Kripke structure K and a safety property globally P, we obtain the following propositional formula. We have the initial state, which is basically a cube of the literals that describe the initial state or the initial states if there are multiple. Then the transition, this is a typo, this should be transition relation of K, which is encoded in T. And then the bad state, which should not be reachable. And if we find a path to the bad state, then we know that property we do not want to have holds in this bad state. And here now for our example, we want to know if globally not P or not Q hold for the Kripke structure. So we want to know if it is the case that P and Q, the processes P and Q do not access the resources at the same time. If we do one step, then the formula is false, because in one step we cannot reach the problematic state. Here the green thing is the initial state, not P, not Q, so we start in initial state, and P prime and Q prime is the property that we want to show that it does not hold. So we ask if we can reach a state where P and Q are both true, and we ask it if it's the case after one step, and the formula is false. And now if we have the formula with two steps, then the formula becomes true. Yeah, and this is one way of doing bounded model checking. And with this, I would like to conclude for today. In the next lecture, we will see another property, and we will also discuss how a similar idea is used in the context of planning, where an agent can do certain actions, and the question is how to execute the actions in order to reach a certain goal. And we will see that this is a rather similar problem as the bounded model checking problem we have here. In fact, bounded model checking was inspired by planning. So this has, even though this is now a verification topic, it has an AI background. But conceptually, bounded model checking is simpler. Therefore, I presented this first, and next we will see how we can do planning with that. Thank you very much for your attention.